Hydrogen bonds are a type of intermolecular force that exists between molecules that contain HN or HO or HF somewhere within the molecule. Um, so for example, if I were to show you this structure, I would know that this structure would hydrogen bond with another one because it has the OH group. However, if I were to ask you about this one would not hydrogen bond with another because though it has O and H, they're not directly connected to each other. So the ones I'm looking for are HN, HO, and HF somewhere within the molecule. These also are pretty much always in polar molecules. If I were to draw a water molecule, and I'm going to draw it bent how it actually is in 3 dimensions, again, the oxygen has a higher electronegativity, and it ends up being that this side of the molecule is relatively negative, and the H's sides are relatively positive. So if I have another water molecule, the negative side of one is attracted to the positive side of another. And the way that we would indicate a hydrogen bond is generally shown with a dotted line between molecules. So the hydrogen bond is not within a molecule, but it's between two molecules. It has properties of a covalent bond, it has properties of an ionic bond, it has properties of a dipole-dipole. It ends up being that a hydrogen bond or structure that hydrogen bonds is going to be stronger than a dipole-dipole force, which we have already discussed is stronger than a London dispersion force. If I were to rank all of the IMFs from strongest to weakest, network covalent is strongest, then ionic, then hydrogen bonds, dipole-dipole, and London dispersion force. So the consequence of that is we have the weakest IMF here and the strongest IMF up here. Ms. Ellman is going to talk with you in the next couple days about how this gives rise to other properties that allow us to compare them. But simply, the reason we worked so hard on the first day on classifying as polar or non-polar, et cetera, is that's how I figure out where in this category things go. So for example, which has a stronger IMF? I'm going to do 2 examples here. I'm going to compare NH3 and pH3. I'm going to compare Cl2O and Br2. NH3, non-metal, non-metal. I'm going to draw the Lewis structure. Now that I draw the Lewis structure, I see that it is polar, and because it has an HN in it, it's going to have hydrogen bonds. When I draw pH3's Lewis structure, I see that it's just polar. And since it's just polar, my intermolecular force is going to be dipole-dipole. When comparing, hydrogen bonds are stronger than dipole-dipole. Next comparison, Cl2O versus Br2. Br2 I'm going to draw first. But like all of my diatomics, it's going to be nonpolar. And if it's nonpolar, it has LDFs only. Cl2O has this Lewis structure. Which is going to make it polar. And since it doesn't have HN, HO, or HF, it's just dipole-dipole. And dipole-dipoles are stronger than London dispersion forces.